So welcome. And this session we discuss about the properties of the divided differences. And the basic or the obvious property of the divided differences is just comes from the definition that the divided differences are always symmetric functions of the arguments. So property number one, so remember this how we define if you have two arguments x1 and x0, then we define this one as f of x0 minus f of x1 divided by x0 minus x1. But you see, this quotient can as well be written as f of x1 minus f of x0 divided by x1 minus x0. We'll get the same answer if we write it in that form. And so this will be defining, can write it in this form. Similarly, we have first divided difference of x0 and x1 is given by f of x0 minus f of x1 divided by x0 minus x1. This can be written as f of x0 over x0 minus x1 minus f of x1 divided by x0 minus x1, which you can as well rewrite it as f of x0 divided by x0 minus x1 plus f of x1 divided by x1 minus x0. Remember, rearranging this one, factoring out negative, then negative, negative is positive. Also, we can define the second divided difference of arguments x0, x1, x2. So this is the same as given by f x0, x1 minus x1, x2 divided by x0 minus x2. Please note that this notation, this and this one are just the same notations for the second divided difference of arguments x0, x1, and x2. So this can as well be written as 1 over x0 minus x2 into f of x0, x1 minus f x1, x2, which can be written as 1 over x0 minus x2 into, now using the first definition, in this case, remember this is the same thing as writing this notation. Remember, this notation is the same as this. So we write this one as f of x0 divided by x naught minus x1 plus f of x1 divided by x1 minus x naught. And then when you define this one, and because of this factorization of negative, we'll have negative f of x1 over x1 minus x2 plus minus f of x2 divided by x1, x2 minus x1. So this the same definition of the second divided differences of the arguments x0, x1, x2. So this can as well be written as 1 over x0 minus x2 into f of x0 divided by x0 minus x1 plus x1 minus x2 minus x1 minus x0 divided by x1 minus x0 and then x1 minus x2 multiplied by f of x1 minus f of x2 over x2 minus x1. I'll just put these two middle terms together. So when you simplify this, you'll have 1 over x0 minus x2 into brackets f of x0 divided by x0 minus x1 plus x0 minus x2 divided by x1 minus x0 multiplied by x1 minus x2 times f of x1 minus f of x2 divided by x2 minus x1, which will be the same as f of x0 over x0 minus x2 into x0 minus x1, or we can rearrange it, start with x1 and then x2. So put x1, x2. And then plus. So you see when I'm this one and this one cancel out, so I'll have f of x1 divided by x1 minus x0 into x1 minus x2 minus, so we can write it plus f of x2. Remember when I factor out negative here, then I'll have this sign as plus x2 minus x0 and then x2 minus x1. So remember the positive sign is coming now. I'm factoring out because I'll have x0, x2, x2, x1. So factoring out, then I can arrange this one as x2 minus x0. So this is what I'll have. So similarly, we can define other higher order divided differences to show the symmetric nature of the function and the arguments. And then the second property is that if you multiply a constant by the divided difference of a function, then it's the same as the divided difference of that constant times the function itself. So we're saying that the divided differences of the product of a constant and a function is equal to the product of the constant and the divided difference of the function. So this is really what we mean, that the divided difference of a constant k times a function f of x is the same as k times the divided difference of the function. This is a very easy result to prove because we know that. So quick proof. If we define the divided difference of k f of x, then by definition, this will be k f of x naught minus k f at x1 divided by x naught minus x1. So we are defining the divided difference at arguments x0 and x1. So which can as well be written as k into and you see this is just the definition of the divided difference of the function at x0, x1. So it gets the same as k divided difference of the function. So therefore, this result is true for any given constant k. And then number 3, if you define the divided difference of a sum or difference of two functions, then you get the same result to the sum or difference of the corresponding separate divided differences. So this is to mean that if we have a function f of x given by g of x plus h of x, then if we define the first, say, divided difference of the function at x0 and x1, then the same thing as defining, actually this can make this plus or minus g x0 x1 plus or minus h x0 x1. So we can as well also prove this one for the case of addition. So I have f of x given by the sum of g and h. So if I want to define f of x0 x1, then it's the same as f of x0 minus f of x1 divided by x0 minus x1. This is by definition, which is the same thing as now, because f is given by g plus h, so this is the same as writing g of x0 plus h of x0 minus g at x1 plus h at x1. And then I divide this one by x0 minus x1, which will be now opening brackets, g of x0 plus h of x0 minus g of x1 minus h of x1. We divide everything by x0 minus x1. Now putting like functions together, so we have g of x0 minus g of x1 plus h of x0 minus h of x1. Then we divide this one by x0 minus x1. And you see, once I have this, there's no mistake by me putting brackets here and me putting brackets at this point. And you remember a plus b over c can be written as a over c plus b over c. So this will just be g of x0 minus g of x1 divided by x0 minus x1 plus h of x0 minus h of x1 divided by x0 minus x1. And this first expression is the definition of g, the first divided difference of g at x0 x1, and this one is h x0 x1, which is the first divided difference of f at x0 and x1. So a similar result for the difference can as well be obtained using the same approach. And then last property for the divided difference, the nth order divided differences of a polynomial of degree n and x are constants. So you have a polynomial f of x of degree n, then you define the end when you get the divided differences, then the end differences will always be constants. We saw the same actually was applying for the case of the finite differences. So once you know those properties, you'll be able now to solve some problems on divided differences, especially on how to use divided differences to obtain an interpolating polynomial to a given problem. So next session, we'll discuss on how to carry out interpolation by divided differences method. Thank you.